Hey, hello and welcome everybody. This is going to be the kind of the second section on differential equations of this course. The title is called Second Order Linear Homogeneous Constant Coefficient Ordinary Differential Equations. And so we have a lot of the same adjectives that we saw before, primary difference being the order here. So we've moved away from first order, and now we're on second order. And if you recall, the order of a differential equation is the highest number of derivatives taken. In the past, our differential equations were like x1 prime was 2x1 plus x2, and x2 prime was x1 minus 2x2. We had some initial conditions maybe as well. x1 at time 0 was 1, x2 at time 0 was negative 2 or something. So this is first order, since highest number of derivatives is 1. Today we'll be looking at second order, but we're not going to be looking at systems. We won't address second order systems, meaning there was a system because we had really two variables, x1 and x2, that we would end up solving for. So we won't be addressing systems, we'll only address a single variable, but in second order, we'll just do one dependent variable. But in second order, what we're thinking, especially when we're using these extra adjectives of linear, homogeneous, and constant coefficient, they're all going to be taking the form. They'll take the form a y double prime plus b y prime plus cy equals. I can write equals d on the right hand side, but in general, to be homogeneous, this should just be equal to 0. So we'll say a y double prime plus by prime plus cy equals 0 will be the ODEs we analyze. And in terms of extra conditions, in the first order case, we had our two initial conditions. We could potentially have two initial conditions here as well. We could have y at time 0 equals y0, and y prime at time 0 equals y1 maybe. That's perfectly valid. This would be an initial condition of our initial position and our initial velocity, the first time derivative, as well as the differential equation itself would relate acceleration relates to velocity and position. So that's one interpretation of a second order constant coefficient linear PDE. Another one, we could have something, this is called an initial value problem, also known as IVP, because the two terms that are given to us, provided to us, are initial conditions. Or you could have something where the actual ODE looks the same, so still a y double prime plus by prime plus cy equals 0, but instead of having an initial condition and an initial velocity, we actually call these boundary value problems, where the function takes on two values, or my solution takes two values prescribed at different points in space. So the way I like to think about maybe the primary difference between these two is an initial value problem describes trajectories. So think about like a cannon. Here's my little cannon, if I can be a good drawer today. There's a cannon. That looks like a cannon, right? Sure. So I've got a cannon here. And basically the idea is if we understand the cannonball's initial position, the position is the same as the position of the cannon, as well as an initial velocity, which comes from, the force of the explosion. And the position just comes from the cannon itself. Then we should be able to describe where the cannonball ends up. This is really projectile motion. That's what an initial value problem describes for us. A boundary value problem more or less, which we call BVP, describes the height of an object extended throughout space. And this is really why I'm using an x as my variables there, x to denote a spatial variable, t is my variable up here, t to denote a temporal or time variable. So the boundary value problem describes the height of an object extended through space. My favorite example is just a bridge. So I've got some canyon over here. Maybe it's got some water on it. This is a river cutting a canyon. And we may be really interested in building a bridge. And so we go ahead and build a bridge, which sags a little bit underneath its own weight. Sags under its own weight. But suppose we want to describe the height of the bridge over the canyon. The height of the bridge can be described by this y once we solve the equation, because you can think about y double prime really as a curvature related to a slope related to the height. So that's how you relate the three terms spatially. And it's a boundary value problem because both sides of the bridge are prescribed. You don't really have a choice over that specific height. They're going to be whatever they are. So that's really the two second order systems, not even systems, second order ODEs in a non-system sense. So really what we have, linear and constant coefficient just corresponds to that A, B, and C don't depend on my independent variable. And homogeneous is the 0 on the far right side. So we're going to analyze equations of these forms today. I'm going to start out and take a little detour. And a lot of people don't take this detour when they teach it. Detour is going to be extracting the solution to a y double prime plus b y prime plus cy equals 0 from our system of first order solutions, which you'll recall take the form, let's say z over time equals e to the t m acting on z at time 0, or something like that, right? It's the matrix exponential solution. So a lot of people don't go through this process, but I think it's a bit of an enlightening process to extract the solution to the equation we're going to study today, coming from the solution that we've already been looking at. So let's go ahead and do that. Let's go ahead and extract that solution. And actually, I'll give myself some initial time value. Let's actually just call it 0, y0, and some initial velocity at 0, y1. So how could we do this? What we do is we define the vector z, which evolves over time, to have two components. It's going to have y, which is really what I'm searching for in my original ODE, and I'm also going to take a derivative of y as my second component. So the second component to z is the first derivative of y. Second component to this vector is the first derivative of our solution. Whatever our solution may be, we don't know what it is yet. But I'm also going to give these the name z1 of time and z2 of time. So in some sense, I'm attributing a y. I'm going to replace it with a z1. I'm going to replace y prime with a z2. What this does to the original ODE that we're focused on is we can go ahead and replace each y. So there's a y sitting right here. We can replace that with z1. So I'm going to go ahead and replace that y with z1. I can replace the y prime sitting right here with z2. So I'll go ahead and do that. z2. And I can replace the y right there with z1 and the y prime right there with z2. So it looks like I have a z1 at time 0 is y0, and z2 at time 0 is y1. Just replaced every y and y prime with z1 and z2. And the only term I haven't replaced is this y double prime. So that's maybe the tricky term. What should I do with that y double prime? Well, if y prime equals z1, or sorry, z2, then y double prime must just be the first derivative of z2. It's got to be z2 prime, right? I mean, I'm just adding a derivative to both sides of my equation. This has to be z2 prime. So what I've done, just by making this choice over a name, all that z was a name. What's in a name? All I've done is now I've reduced second order ODE to a first order ODE. But the price I'm paying is that the second order ODE had one dependent variable. The dependent variable was y. The first order ODE has two dependent variables. So you can play this game of trading orders for variables. That's really what's happened here. We've played the game of trading an order for variables, but we know how to handle the two dependent variables first orders. These are systems of first order ODEs. So that's all of a sudden what we ended up on the left-hand side is something of the form that we can tackle. Now it's not quite of the form that we can tackle, right? Because what we actually want, what we know how to solve, would be something like z1 prime equals something, z2 prime equals something, and then z1 at time 0, we can just extract that at the very least from directly from above. z1 at time 0 is y0, z2 at time 0 is y1. But the big question is, we know how to solve these sorts of systems. What should these question marks be? We're close. Everything up here is close to a question mark, but not quite. All right, so what's happened below is that we've solved explicitly for z2 prime. So let's go ahead and grab this and rearrange for z2 prime equals something. Well, we can rearrange that just by subtracting bz2 and cz1 to the right-hand side, as well as dividing by a z2. Well, really just a, dividing by a, because we can keep z2 prime around. So we're going to have a negative bz2, negative cz1 on the right-hand side, and we'll be dividing everything by a, or if I rearrange that a little bit to look a little prettier, negative c divided by a, z1, minus b divided by a, z2. I can solve for z2 prime by going through that procedure. Hence I have negative c over a, z1, minus b over a, z2. All I'm missing from my first order system is something to go against z1 prime. Is there any way I can figure out what z1 prime may be equal to? Let's recall what z1 is. Recall z1 was defined to be y. That's the very first thing I did up top. z1 and y were the same. So z1 prime equals y prime. I'm just going to take a derivative of both sides. But wait a minute, y prime is z2. And now that I know that z1 prime is y prime, which also happens to be z2, I know that z1 prime is z2. Or if I really want to make this look like a matrix, 0 copies of z1 plus 1 copy of z2. So this, all of a sudden, is a first order system of ODEs that is 100% equivalent to the second order non-system of ODEs I wanted to start with. Equivalent in the sense that all I've done is changed some names around for y and y prime. So let's go ahead and solve this. We know how to solve this. And in fact, the solution has to be that the vector z evolving over time is e to the t times a matrix. What's my matrix? 0, 1, negative c over a, negative b over a, acting on the initial vector, which was y0, y1. So let's go ahead and compute this matrix exponential. You may be worried that we won't be able to find a computation for it, but we will. Let's go ahead and compute the matrix exponential by diagonalizing 0, 1, negative c over a, negative b over a. What do I need to do to diagonalize? Start with eigenvalues. And I'm going to use the determinant of 0 minus lambda 1, negative c over a, and negative b over a minus lambda. That's going to be negative lambda times negative b over a minus lambda. And then I'll be subtracting c over a times 1, also known as adding c over a. If I distribute the negative lambda to both terms, I'll end up with a lambda squared plus b over a lambda plus c over a. Let's say this is equal to 0. Let's go ahead and multiply both sides by a to simplify things. what do we get? A lambda squared plus b lambda plus c equals 0. This looks exactly like the generic quadratic formula. If I go up to the original equation, I just have a y double prime that's almost like lambda squared, b y prime that's almost like b lambda, c y that's almost like just c lambda to the 0 power. This characteristic equation really just looks exactly like the original ODE I was trying to solve, but I've replaced each of the y's and y primes with lambda to their special power. So that's pretty cool. Let's go ahead and use the quadratic formula on that. It tells me that lambda equals plus or minus negative b plus or minus the square root of b squared minus 4ac all over 2a. It's exactly the quadratic formula that we're always used to, which means that the eigenvalues are exactly those two values of lambda. Now I'm going to jump the gun here, and I'm going to say something about matrix exponentials. Given two eigenvalues, matrix exponentials always look like, let's say e to the tm, it always looks like a constant times e to the lambda 1 t, and then another constant e to the lambda 2t. These are added together, and then you'll get another constant e to the lambda 1t, and yet another constant e to the lambda 2t, as well as some stuff in the bottom row. But I just want to pay attention to that. The matrix exponential always looks like a collection of constants times the exponential to the eigenvalues times t, and that comes directly from the fact that we take e to the t diagonal, where d is just the diagonal of lambda 1 and lambda 2. It's just the diagonal of the two eigenvalues. And so because of that, we always know that the matrix exponential takes this form. And I'm claiming this is enough. This is enough for us to solve our differential equation. So once we know the matrix exponential takes that form, we will actually be able to solve our differential equation. I'll show you why right now. Hence consider e to the tm on our initial vector y0, y1. This is just going to be c1 e to the lambda 1 t plus c2 e to the lambda 2 t, c3 e to the lambda 1 t plus c4 e to the lambda 2 t, and then some dots here. Acting on the vector y0, y1, the output, if I look horizontally against the vertical vector, the output's going to give me c1 y0 plus c3 y1 e to the lambda 1 t, and it's going to give me c2 y0 plus c4 y1 e to the lambda 2 t. And then it's going to give me some dots in my second row. And I claim I only care about the first row. Why do I only care about the first row? Because this is equal to the vector z, the solution to the system, but the vector z has two rows to it, z1 and z2. z1 is equal to y, the original solution to my ODE. z2 doesn't matter because I didn't care about the derivative of the solution. I only care about the solution itself. So the solution to the ODE is the first row. Solution to ODE I care about is the first row, since z as a vector was equal to y, y prime. So that first row is the solution to my ODE as long as I know my eigenvalues, but I do know my eigenvalues, they're right here. So I know that lambda 1 is the one associated to the plus sign, and lambda 2 is the one associated to the minus sign. That is to say, the solution to the ODE, ay double prime plus by prime plus cy equals 0, and sure, we'll go ahead and give it its initial conditions, y0 and y1, is the first row above. It's c1 y0 plus c2 y1 e to the lambda, keep in mind lambda is negative b plus or minus the square root of b squared minus 4ac all over 2a. So e to the negative b plus the square root of b squared minus 4ac divided by 2a t, and then plus c2, this was a c3, c2 y0 plus c4 y1 e to the other eigenvalue, negative b minus the square root b squared minus 4ac, all divided by 2a, and then t. This is my solution, y evolving over time. The only problem is that this is true for some choice of C1, C2, C3, C4, which we must find. But that's okay. It's not that hard to go ahead and find four constants. You find them from evaluating y at 0 and forcing it to be equal to y0, as well as y prime at 0 and forcing it to be equal to y1. We can actually make our lives even easier than this. Because these are arbitrary, basically by choosing any C1 or C3 you would want, you could force that to be any number you want. Let's just forget about calling these C1, C2, C3, C4. What we actually know is that it's some constant against the first E, it's some constant against the second E, and we don't have to worry about C3 or C4. So we just have to find C1 and C2, which can meet our initial conditions for us. This is the solution to the second order linear problem. So I'm going to mention that now. I'll write it as a theorem. Solution to really just a y double prime plus by prime plus cy equals 0 is given by y of t is equal to c1 e to the unfortunate quadratic formula b plus or minus square root of b squared minus 4ac all divided by 2a t plus c2 e to the negative b minus the square root of b squared minus 4ac all over 2a t. Now there's a caveat. This is true when b squared is not equal to 4ac. If b squared equals 4ac, there's an extra thing that happens. And what happens is you have repeated roots, and that gets into the case when your exponential is not actually diagonalizable. Your matrix isn't diagonalizable. We end up with the following. We get c1 e to the negative b over 2a t, and we get c2 times t e to the negative b over 2a t. So it gets a little bit more complicated. What I'll do is write this as a piecewise function now, just because of that repeated roots problem. And then you lose diagonalizability of the matrix. And you all saw what it was like to have a non-diagonalizable matrix. But this is what you should be taking away from what we've accomplished so far today. And now we can just go ahead and use this anytime somebody asks us to solve a given second order problem. And I'd also want to mention, a lot of times we won't use the variable t in second order because when it's a boundary value problem, we're working over space. So you may also be required to put an x in here instead. And that includes this t. So I'll actually write it in terms of x. Just be aware that you can use either a t or an x in these problems, depending on if you're a boundary or initial value problem. So let's just go through one for today, and then we can work through some in the next video. Let's do a boundary value problem. So let's go ahead and solve y double prime plus 2y prime plus 2 equals 0, where y at spatial point 0 is equal to 1, and y at spatial point 1 is equal to 1. So let's see if we can find a solution here. Using our formula from above, we first compute b squared and check if it's equal to 4ac. That's 4ac. In this case, b is 2, so we're doing 2 squared. Now we're checking if that's equal to 4 times 1 times 2 is going to be 4 times 1 times 2. So that's equal to 8. 2 squared is equal to 4. And so they are not equal. And when they're not equal, we can go ahead and work with our top case, which is kind of the generic case. And so we immediately have that our solution takes the form y of x is equal to the top row. Okay, so we're looking at that top row because b squared is not equal to 4ac. c1 e to the negative b, so negative 2, plus the square root of b squared is 4 minus 4ac is 4 minus 8, all divided by 2, x plus c2 e to the negative b minus the square root of 4 minus 8 all over 2x. And if I want to simplify those exponents, it looks like I have a square root of negative 4. Square root of negative 4 is going to be 2i because of a negative number, all divided by 2. And then e to the negative 2 minus 2i, all divided by 2. If I distribute the 2 in the denominator to both 2's in the numerator, it looks like I have c1 e to the negative 1 plus I x, and c2 e to the negative 1 minus I x. If we want to, we could use Euler's formula and simplify this in terms of cosine and sine. I'm not going to. It's usually not to our advantage unless you really care about cosine and sine. So we could use Euler's formula and rearrange in terms of sine and cosine. I really don't want to. I'm satisfied with what it looks like right now. But there's always a second step here. And maybe I'll call this the third step, because the second step is that the solution takes this form. The third step, we must find C1 and C2 from the conditions. What are the conditions in this problem? y0 equals 1, y1 equals 1. So the conditions were that y at 0 equals 1 and y at 1 equals 1. So let's just plug in. We do this by plugging in both 0 and 1 to our solution. So when I plug in 0 to my solution, that's this one. I'm plugging in 0 for x. C1 e to the negative 1 minus or plus I times 0 plus C2 e to the negative 1 minus I times 0. Everything to the 0 power is always 1. This gives me C1 plus C2. But I know that this is supposed to be equal to 1. So because I have, from the condition this is equal to 1, I've established one relationship between C1 and C2. The second condition is going to give me a second relationship. So let's go ahead and plug in 1. I have C1 e to the negative 1 plus I. I'm plugging in 1 for x because of the 1 there. C2 e to the negative 1 minus I. I'm plugging in 1 for x because of the 1 there. And this just equals what it equals. It's C1 e to the negative 1 plus I plus C2 e to the negative 1 minus I equals, I know what this is equal to because of the second condition there. So that has to also be equal to 1. And what I'm left with is a system of two equations and two unknowns. Those unknowns are C1 and C2. So maybe I'll go ahead and write it like a system. The system C1 plus C2 equals 1. I have C1 e to the negative 1 plus I plus C2 e to the negative 1 minus I equals 1. Now, these are ugly, but they do just have to come along for the ride. They are numbers, right? There's Euler's number to a complex number. It's a perfectly well-defined number. So we just have to get comfortable playing substitution method games, even with ugly coefficients. I can solve the first for C1. That's going to tell me C1 is 1 minus C2. I go ahead and plug that in for C1 in the second case. Plug in C1. Where does that send me? It sends me to 1 minus C2 e to the negative 1 plus I plus C2 e to the positive, or 1 minus I equals 0. I just have to go through lovely algebra, solve for C2. It looks like I can do that by distributing that exponential. So I'll have e to the negative 1 plus I minus C2 e to the negative 1 plus I plus C2 e to the negative 1 minus I equals 0. I can go ahead and move this to the right-hand side and factor out a C2. That's going to give me C2. And then I have really a negative copy of e to the minus 1 plus I. I have a positive copy of e to the minus 1 minus I. That's equal to negative e to the negative 1 plus I. And then I can finish off by dividing everything by negative e to the negative 1 plus I plus e to the negative 1 minus I to both sides. And I'm left with C2 is equal to, I'll let the negatives cancel at the price of making that term negative. I have the ratio of e to the minus 1 plus I divided by e to the minus 1 plus I minus e to the minus 1 minus I. I could simplify this if I wanted to. It actually simplifies okay because you can multiply exponentials by the negative exponents to cancel them. So I can multiply both the numerator and denominator. But keep in mind, I never make you simplify in this course if you don't want to. But those will cancel because the exponents add up to 1, or add up to 0, so we just get e to the 0 power. And then if I distribute this to both terms, you'll notice that actually it cancels in the term on the left, and the 1 and negative 1 cancel with the term on the right. I'm left with 1 minus e to the, so the 1 and the negative 1 cancel, I just have 2 copies of negative I. So it does simplify just a tad to that number. And then now that we know what C2 is equal to, we can go ahead and plug C2 into that formula for C1. That's going to give me that C1 is equal to 1 minus this object, 1 divided by 1 minus e to the negative 2I. And then if I want to do common denominator, I certainly could. Common denominator here would be to take that and replace it with the denominator on the right, the numerator over the denominator, because then I'm subtracting 1 from both the numerator and denominator. And what happens when I subtract 1 from the numerator is that 1 will cancel with that 1, and I'm just going to be left with C1 is negative e to the negative 2I divided by 1 minus e to the negative 2I. Okay, so the numbers aren't pretty. That is life. If numbers were only pretty in life, we would be living in a utopia. Last time I checked, we're not. So those two numbers are what they are, and they get plugged in for C1 and C2. So we'll go ahead and plug those numbers in to our actual solution formula. Our solution was y as a function of x was C1, which I'm going to grab C1. So negative e to the negative 2I divided by 1 minus e to the negative 2I. So C1 times e to the negative 1 plus I x plus C2, which is 1 divided by 1 minus e to the negative 2I against e to the negative 1 minus I x. And this is the final solution to the ODE. This could still be simplified in terms of sines and cosines. You'll notice that since the original ODE here has only real coefficients, this solution will in fact be real. It just doesn't look like it's real in its current form. But we're not going to go ahead and simplify that. Like I said before, I never really expect you to simplify if you don't want to. You can definitely make your life harder rather than easier if you don't know what you're doing. Anyway, I'll see you in the next class where we'll get a lot more practice with these. Bye.